Thank you, Laura. And thank you also to Maria and Oliver and Ian for inviting me to speak here. So this is joint work with Jeremy Martin, Jennifer Wagner, and Jose Zamora. Jeremy and Jennifer were like doing a sabbatical last year in Santiago with us and with the Colombians that you already know. And so the first part is going to be a little introduction to the chromatic symmetric function. And so I have heard that Matthias already did a little talk about this, so hopefully this will be quick. And then the two remaining parts are going to be about our work. Okay, so we start by the basic definition, what a proper coloring is. So if I have a graph with n vertices, I'm going to color the vertices in such a way that whenever I have two vertices that are connected by an edge, and then I have different colors. So I'm trying to, what I did something wrong here. No, it's okay. Okay, so this is a little example. If you look at the example at the graph on the right, and the numbers are the colors, then you see that there an edge that is monochromatic with color 1, and so this is the coloring in the right is not a proper coloring, while the coloring on the left, it is a proper coloring. Okay, and so with this, we define the chromatic symmetric function, which is basically a generating sum over all proper colorings. It's an infinite sum, of course. And so for each coloring, we count how many times the color is being used. And then this is encoded in a monomial. And since we're summing over all colorings, if we do a permutation of the colorings, I still get a proper coloring. And so I get a generalization of the chromatic polynomial. I'm not going to recall the definition of chromatic polynomial. And this function was introduced by Stanley on 1995. And so very basic stuff about symmetric functions is that, we already said it, a symmetric function is a power series that is invariant under permutations. Most of the time, partitions are being used to index symmetric functions, and we have two basic symmetric functions that are bases. So one is the monomial basis, that is like I take, given a partition lambda, I take all the monomials that have lambda in the exponents, and then I take all this all the symmetric version of those monomials, and then the power sum is just take the one variable power k, and then I take all the symmetric versions of those, and we know that those are bases for the symmetric functions. And so in order to get an idea what this function looks like, the basic theorem by Stanley says that you can compute the power sum expansion by this formula. So basically you do a sum over all subset of edges, and then you have to consider a partition, that is the partition of the connected, given by the sizes of the connected components of G restricted to A. So an example, if I take this graph on the, so let me see if this works. So I have this graph here. And then if I take the partition, so this is the empty set of edges, then the, I don't know, cyan color is telling you what the edges that are being selected are. So in the first row, we have one edge being selected. In the second row, we have two edges being selected. And in the third row, we have all of the three edges being selected. And so with those edges selected, we see what are the induced subgraphs. So this gives us this connected component. So if I have no edge selected, then everything is an isolated vertex. So I have 4 isolated vertices. So I have a partition 1 power 4. So I get the corresponding term P1 over 4. And since the size of no edges is 0, then I have a positive sign. Then when I go here, I will get negative sign, and here we go positive sign, and then I will have negative signs. And I have this. So when I have, for instance, in this case, I will have 1 connected component with 2, and 2 connected components with 1. So I get the partition 2, 1 square. And so I will get minus 3p to 1 square plus 3p3 minus p4. And so this is going to be the chromatic symmetric function of the star with 4 vertices. Is this clear? Yes. So we can also do it for the path. And so if we do it for the path, we will see a difference, because for the path here, we will see that there is a partition into 2 connecting components with 2 vertices. So in this case, I will have P14 minus 3p21 square plus 2p31 plus p21 minus p4. So I will have this, sorry, 2. I will have this difference in the chromatic symmetric function with respect to the previous, here we had 3 and then 3p31. So now I have 2p31, and the partition that is new is this partition 2. Okay. So one basic fact is that we know that if we have graphs with cycles, then we can construct graphs with the same chromatic symmetry function that are not isomorphic. So this is the basic example given by Stalin in the first paper about the chromatic symmetry function. And then the basic question that is often referred to Stalin is that whether we have or not non-isomorphic trees with the same chromatic symmetric function. This is a widely open question, and the idea of the talk here is like try to give you why my opinion is that it's not possible to find non-isomorphic trees with the same chromatic symmetry function. And so I will put it into 2 different problems that are almost the same problem, but are not exactly the same problem. So the one is whether, so the first is the tree isomorphism conjecture that says that if you have trees that have the same symmetric chromatic function, they have to be isomorphic. And then the next one would be the reconstruction conjecture that says that actually, if you know the chromatic symmetric function of a tree, then you can reconstruct the tree up to isomorphism. That's a little bit stronger, okay, than the first one. And so actually, for instance, what are the known results about this? This is a non-complete list. So for caterpillars and spiders, there are various results by myself and Zamora, by Level and Sereni, and by Jennifer and Jeremy and Matthew Moran for these classes of graphs. For trees up to 29 vertices, it was verified in the computer by Hale and G. And then for trees of diameter up to 5, recently Rosa Orellana with 2 students, Mario Gonzalez, and I think both are called Mario Gonzalez and Mario Tomba. They did it, and what is important is that this here, they have an algorithm to reconstruct the tree. So if you give them the chromatic symmetry function of a tree of diameter up to 5, then they give you back the tree up to isomorphism, which is not the same here. Here, what they did was like really check pairs of trees up to 29 vertices, and they checked that no pair of trees have the same chromatic symmetry function, which is slightly less strong. And then also I just mentioned there was a poster by Sagar Sawant that also is talking about that. Okay, so completely non-complete list. And then this gives us two motivating questions for this talk. Okay, so we are okay in the 10-minute mark. So if I have another tree invariant, like not the chromatic symmetry function, but another, like the chromatic polynomial or the degree sequence or another tree invariant, if it's true, is it true that I can compute this invariant from the knowledge of the chromatic symmetry function, and whether we can characterize non-isomorphic trees with the same invariant? Okay, these are two motivating questions that give us some ideas of whether these conjectures can be true or not. Okay, and so I'm going to talk about what we did like 6 months ago with Jeremy and Jennifer and Jose. And so first I will recall to you what the subtree polynomial is. So the idea is that we're going to count, given a tree, we're going to count how many trees with a certain number of edges and a certain number of leaves do we have. So this is done typically in a generating function. So this generating function is given here. So I'm just using two variables, q to enumerate the number of edges and r to enumerate the number of leaves. And so this variable, this function, this polynomial is counting how many subtrees do we have. And all my examples are very small because otherwise they're very heavy to compute. So if we do it for the star with 4 vertices, then you can check that these are all the possible subtrees with more than one edge. And then, of course, these are the correct numbers. Like, so I have three subtrees with one edge. I have 3 subtrees with 2 edges, and then I have only one subtree with 3 edges. So this gives us this generating function here. And actually, I can just factorize it and have it this. And you can prove actually that for any star with n vertices, you have this form. So it's not very difficult to prove this form. Okay. Where do I put? Yes, it should be S instead of A. That's a typo. Thank you. And here as well. So the thing is that Jeremy with Jennifer and Matthew, they proved in 2008 that actually you can compute the subtree polynomial directly from the chromatic symmetric function. Here I forgot to mention that x of t, I'm writing it like c lambda of t, p lambda, lambda partitions of n. So if I take the coefficients of the chromatic symmetry function in the p lambda expansion, and then there will be a formula that I'm not going to give you because it's tricky to give the formula, that where the important thing is that this sum, this function does not depend on t. So this basically saying that you can linearly compute the subtree polynomial from the chromatic symmetry function. Okay. So in 2020, Logan crew defined a generalization of the degree polynomial. And so instead of counting by subtrees, he counts all subsets of vertices. And so he counts how many edges have one endpoint, should be endpoint there in A, and how many edges have 2 endpoints in A. And so I'm going to get a generating function with these 3 parameters. Okay. And so this is like a little slightly more general polynomial. And so he conjectured that actually you can do the same thing. You can determine this polynomial GDP from the chromatic symmetric function. Okay. So I will give an example of this in a moment. Okay. And then Wang Yu and Chang, I don't know if I'm pronouncing it right, they wanted to solve this conjecture by Logan, but they could not. They did like a partial result where they only did a partial version of the generalized degree polynomial. So they define this is half generalized, which is like if I take the Q polynomial and I take only the terms of this form and I evaluate them in x equal to 1, I get this polynomial. So of course it's a invariant that is not as powerful as the GDP. And actually they show that you can determine this polynomial from the chromatic symmetric function. And so an example in order to get an idea of how these invariants all are. And so for instance, if I take A, so A is going to be the red or purple vertices. So I can take first A equal to empty set. So if A is equal to empty set, I get only 0, so I get a 1 as a term. If I get, for instance, one vertex that is in the center of the star, I will have, of course, it has only one vertex, but it has 3 edges that have one endpoint in the center and 0 edges that have both endpoints in the center. And if I take a leaf, it's going to be, since it's a leaf, it's only one vertex. So you can, if you think a little bit about it, you can see that these tables make sense and it gives you this polynomial here. And then if the purple terms are the terms that satisfy that x, the power of x is 1 more than the power of c. And so then I evaluate them to 1. So for instance, if I take this and I make x equal to 1, I get y power third and so on. So these are the terms that are going to give us the half generalized degree polynomial, and then I will have the subtree polynomial that we already compute, and then we have the chromatic symmetric function that we already compute. Okay. So I don't know if there are more questions. Okay, so so let us stop a little bit. Hopefully you got an idea of what these invariants mean. And so we have, on the top, we have the chromatic symmetric function. And then we know that, so we prove now, this is Crew conjecture. And so this is one of the main results of that we prove here. And subtree polynomial was already proved by Jeremy, Moran, and Jennifer in 2008. And this is the other thing I mentioned. And so, of course, this we know because it was defined as something that is simpler. So basically, what we showed in this paper is these two edges. Like we show that first, that the Crew conjecture is true, and then we show that actually this half generalized degree polynomial and the subtree polynomial, they're equivalent. Like you can go from one to the other. Okay. So we are in the 20-minute mark. So I have good. So so here I'm not going to give more details. If there are some questions at the end, I could give a little detail that I'm not going to have enough time, most probably. So the second question was like, if I have an invariant, can I characterize non-isomorphic trees with the same value of the invariant? So there's in graph polynomials and in graph invariants, there are a lot of papers where people try to solve this question for different invariants, like graphs that have the same chromatic polynomial, graphs that have the same tag polynomial, matroids that have the same tag polynomial, and so on and so on and so on. So for instance, Gordon and Eisenstadt in 2009, they proved that these caterpillars here, these graphs here, where this here means that I have A leaves like this. Here I have B minus 1 leaves, A minus 1, A plus B minus 1, B leaves. So you can see that these two graphs are not isomorphic if A is different from B, then these graphs are not isomorphic, but they have the same subtree polynomial. So that means that the conjecture of whether, or the question of whether trees with the same subtree polynomial have to be isomorphic is, the answer is no. We have a counterexample to this. Okay, so this was proved in 2009. So I will, in the next 10 minutes, I will try to explain to you how do we do to prove this in an algebraic way. So I will mention that the proof, the original proof is not very difficult, it's not super difficult. It's nice, it's a combinatorial proof. And now what we did is to give a algebraic proof. So what we can show is that actually there is a recursion for the half generalized polynomial. So first we have to make a little adaptation, that we have to subtract this term that actually is counting like trivial trees. So we don't want to count these trivial trees that don't contain internal vertices of T. And then we need to introduce an operation that's called near contraction. So the basic idea of near contraction is that I'm going to contract this edge, but I'm going to some kind of transform it into a new edge. So basically I contract and then I add a leaf in the vertex I contracted. Okay, I don't know if it's clear, the near contraction. And so what we showed with in our paper is that actually if you have, and I think I have to go to the next one because it's the same idea, is that if I have a tree, like maybe so I have a tree T1, then I have an edge here, and then I have a T1 and T2. So then I can split this computation in terms of 3 different graphs. So I will do it. I will use this proposition in order to show this corollary in an algebraic way. So the idea, and with that, hopefully it will be easy to understand what the formula means. So the formula is saying that if I apply, this is going to be T1, this is my edge, and this is T2. So what it's saying is that I will have T1 plus an edge, T2 plus an edge, and here I will have the near contraction. Okay, and so the near contraction, I will contract and then I will add 1 leaf. So if you see where I contracted here where I have B minus 1 leaves and A minus 1 leaves. So basically I will have, when I contract, I will have A plus B minus 2. But since I added this leaf, this basically has A plus B minus 1 leaves. And here I have A minus 1 leaf, but since I have this leaf here, basically I have A leaves here. And the same here, I have B minus 1 leaves, so I have B leaves. Okay, so unfortunately, let me see if I can. It's not so. Okay. So if I do the same for the other graph, that I'm sorry, my Zoom is not working, it's just getting with this thing there. Then you will see that you have, so here you have A plus B minus 1, B, and downstairs you have B, A plus B minus 1, A. So you have isomorphic trees here, isomorphic trees here. So sorry, you have isomorphic trees here, isomorphic trees here, and isomorphic trees here. So that means that these two graphs, actually, they have the same polynomials, okay? So that's a very basic proof, algebraic proof that this thing have the same polynomial. Then Gordon and Eisenstadt did a conjecture. I will go over this because most probably I have 5 minutes, so hopefully I will able to explain this. So I will expand. So this conjecture of Gordon and Eisenstadt is for caterpillars. So we know that caterpillars are trees that where I delete all the leaves, I get a path. And then what we know is that if I have caterpillars, I can see caterpillars are as integer compositions up to reversal. Sorry. So for instance, this, I have 2 vertices, 3 vertices, 2 vertices, 1 vertex, and 3 vertex. So I have this composition here. So I have a bijection between compositions and caterpillars, and I have 3 operations for compositions. The first concatenation is classical. Near concatenation is also classical and used in ribbon short functions. Basically, I just add the overlaps. And then there is a new one that actually was defined by Vilera and Van Willigenburg and Thomas in 2006, where basically what I do is like, I say, okay, 1, 2 is going to be repeated, but how I'm going to repeat 1, 2 is encoded by this composition. So this 1 means that first I will put 1 copy of 1, 2. This 2 means that I'm going to put 2 copies of 1, 2 that are going to be joined by a near concatenation. And then this 3 here means that I'm going to put 3 copies of 1, 2 that are going to be joined by near concatenation. So like this, I define this new operation that's called composition, and I get this operation. And with that, what is amazing is this result by Vilera, Van Willigenburg, and Thomas, is that actually there is a unique there is a notion of factorization for this product, and with this factorization, we know that every composition admits a unique factorization. I have to go over in order to be able to finish, and then I will say that a switch of a composition is like if I have the unique factorization of a composition, a switching is like reversing any of these factors. And what we show is that actually, if we reverse these factors, it doesn't change the polynomial. And so basically it's saying that switching implies, related by switching implies the same polynomial. But the question is whether we can go back, and that's an open question. And so this is where I wanted to arrive. So I have 1 minute. So I want to explain a little bit about this thing, and I will end with this. So the recursion that we proved before, actually, when you apply to caterpillars, give you a closed formula. And this closed formula is written here. Okay, but what is important about this closed formula is that it's given in terms of coordinates of my composition alpha. So for instance, if I get 314 as a composition, I get 442 because I add the 3 and the 1. I get 352 because I add the 1 and the 4. I get 316 because I add the 4 and the 2, and so on. Okay, so I get the whole lattice of coordinates, and then I sort. So for instance, here I get 631, 532, 442, and so on. So I get the partitions of these coordinates, And this information, this multiset of the partitions induced by the coordinates of my alpha actually determines my polynomial. And this is the amazing result by Vilera, Van Leeuwenhoek, and Thomas, is that actually they classify when two compositions have the same multiset of partitions induced by the coordinates. And they show that if and only that two compositions, they have the same multiset if and only if they're related by switching. So basically, our theorem says, okay, we know that this polynomial comes from this multiset, and we know a classification of this multiset. So basically, this is telling the proof of our theorem. Okay, and I think that's it. Okay, thank you. I went over 1 minute.